18 billion miles from Earth, a dying spacecraft just sent back something that changed everything. Voyager 1, launched before most of us were born, picked up a pressure wave, a magnetic tilt, and a cosmic ray surge none of our models predicted. Something out there is pulling on our solar system. You will see a star aimed straight at us, a ribbon of energy circling the sun, and a cloud we are about to fall into. If wonder still moves you, hit subscribe and stay close. Turn off the lights. We begin. A signal so faint it takes more than 22 hours to reach us just arrived at a radio dish in the Mojave Desert. It came from Voyager 1, the farthest human-made object ever built. Right now, as you hear this, it is drifting through a region no probe has ever touched, sending home a whisper so quiet that engineers describe it as catching the light of a single candle from the other side of the planet. Voyager 1 launched in 1977. It was meant to last 5 years. 5. It is now approaching 50. Its power supply, a small block of plutonium, loses about 4 watts of energy every single year. Engineers have been shutting off instruments one by one, like closing doors in a house before winter, just to keep the lights on a little longer. And yet, it keeps talking. What makes the recent signals so strange is what they are showing. Voyager is not simply fading into quiet space. It is reporting turbulence, pressure, unexpected jolts in the plasma around it. The craft is supposed to be in the calm interstellar medium, a place scientists imagined as smooth and empty. Instead, it is being rattled, shoved, bent by forces the original engineers never planned for. Picture a small glass bottle tossed into the open ocean. That bottle has a tiny voice inside, calling back towards shore. The farther it drifts, the quieter it gets. Now picture that bottle suddenly being pushed sideways by a current no one knew existed. That is what is happening to Voyager. The probe's antenna is locked onto Earth, a dish the size of a small car, pointed with the precision of a sniper, beaming 22 watts of power across the darkness. That is less energy than the bulb in your refrigerator. By the time it reaches us, that signal has thinned into something almost mathematical. Our deep space network has to strain to hear it. Engineers at the Jet Propulsion Laboratory say the spacecraft has been behaving in ways they cannot fully explain. Data streams go briefly scrambled. Orientation drifts. Small anomalies build up. Some of it is age. A machine this old, this cold, this far from the sun, is expected to struggle. But some of it is not age. Some of it is environment. Something is out there. The data points to a boundary region that is not behaving the way textbooks described. Ripples, shock waves. A push coming from a direction our models did not account for. And Voyager, the little bottle in the ocean, is the only eyewitness. Here is the weight of it. Every signal Voyager sends now is a final letter. When the plutonium dies, the probe will keep moving forever, but it will go silent. Whatever it is learning in these last years, whatever warning it is carrying, has to reach us before the battery fades. After that, we are blind. No other spacecraft will be in that region for at least 30 years. So, scientists are listening harder than ever. Every bit of data matters. Every anomaly is studied like a clue at a crime scene, because buried in the noise is a single, unsettling pattern. Our solar system is being pulled, and the next thing Voyager discovered is the wall that almost stopped it. On August 25th, 2012, Voyager 1 slammed into something invisible. The craft did not shake. Nothing broke. No alarms lit up on any console back on Earth. But the numbers coming back told a story that stunned the team at the Jet Propulsion Laboratory. In a matter of hours, the particle counts around the spacecraft changed so dramatically that scientists realized they were watching history happen in real time. Voyager had crossed the heliopause. Think of our sun as a candle inside a massive bubble. The candle's heat and light push outward in every direction, creating a wind of charged particles called the solar wind. That wind travels for billions of miles, carving out a protected pocket in space. The bubble's outer edge is the heliopause. Outside it, the sun's influence ends. Interstellar space begins. For decades, scientists argued about what the edge of that bubble would look like. Would it be smooth, Soft, a gentle fade? The truth was far stranger. Voyager hit a wall of pressure so dense and so sharp that it acted almost like a physical surface. Plasma on one side, a different plasma on the other, and between them, a narrow crossing zone that compressed the probe's readings into chaos. Picture standing at the exact shoreline of an ocean, where the sand is dry one moment and soaking wet the next. Except this shoreline is made of magnetic fields and charged particles, and it sits roughly 11 billion miles from your couch. What made the discovery even more unsettling was the pressure itself. The heliopause pushed back on Voyager harder than any model had predicted. The interstellar medium beyond the bubble is not empty. It is packed with its own particles, its own magnetic tension, its own slow-moving wind of material left over from ancient exploding stars. And that material is pressing inward on our solar system with force. Something is squeezing our bubble. Voyager 2, Voyager 1's sibling, crossed the same boundary 6 years later in a completely different location. And here is where the mystery deepens. The two crossings were not identical. Voyager 2 reported a thicker, more layered wall, a transition zone with ripples and pockets. Voyager 1 passed through fast. Voyager 2 got caught in the churn. That difference matters, because it means the heliopause is not a smooth shell. It is lumpy, uneven, possibly even moving. Scientists now believe the wall flexes. It breathes. Sometimes it pushes out. Sometimes it caves in. And whatever is on the other side is not sitting still. Streams of interstellar particles punch through in places, leaking into the bubble like water finding cracks in a dam. For Earth, the heliopause is a shield. It blocks most of the high-energy radiation coming from deep space. When the bubble gets squeezed, that shield weakens. More cosmic rays get through. More radiation reaches the inner planets. More hits our atmosphere, our satellites, and over long enough timescales, our DNA. Voyager 1 is now beyond that wall. It is swimming in raw interstellar soup, and the readings it sends back suggest the soup is thicker, hotter, and more turbulent than anyone expected. The pressure outside is rising. Right as the probe reported that rising pressure, something hit it from a direction no one had been watching. The first sign came as a sudden spike on a graph. Inside mission control, a scientist watching a routine data stream saw the counter climb, then climb again. Cosmic ray hits on Voyager's detectors were jumping by percentages that should have taken years to appear. They were appearing in days, then hours. Something was bombarding the spacecraft. Cosmic rays are not rays of light. They are pieces of atoms, stripped bare, flung across the galaxy at nearly the speed of light. Most come from exploded stars called supernovae. When one of these particles hits a human body, it punches through cells like a bullet through paper. Our atmosphere and the sun's magnetic bubble protect us from most of them. Voyager has neither shield now. After crossing the heliopause, cosmic ray counts on Voyager jumped by about 25%. The jump matched predictions. Scientists expected a rise once the probe left the sun's protective pocket. What they did not expect came next. The counts kept rising. Not a little, a lot, and the particles hitting the spacecraft were more energetic than the models allowed. Some were arriving from directions that did not make sense. Others carried signatures that hinted at sources far closer than the distant supernovae textbooks assumed. Picture standing in a rainstorm, where every drop is moving at the speed of a rifle bullet. Now imagine the rain starts falling sideways, then diagonally, then from below, the direction of the storm keeps changing, and no one can explain why. That is the pattern Voyager recorded. Scientists at NASA began running simulations. They tried to match the incoming flux to known nearby supernova remnants. Some matched, many did not. A portion of the cosmic rays appeared to be coming from the local neighborhood within a few hundred light years. That implied something recent, something that should still be detectable in other ways. There is a theory gaining traction. A supernova may have gone off near our solar system within the last few million years. Its shockwave is still washing over us. The expanding wave of particles is being compressed by our heliopause, and when Voyager crossed over, it stepped directly into the debris field. This is a theory, not a confirmed fact, but the fingerprints fit. Here is the unsettling part for Earth. Cosmic rays affect our climate. They help form clouds, by seeding water droplets around the particles that slam into our upper atmosphere. More cosmic rays can mean more cloud cover. More cloud cover can cool the planet. Studies have linked long-term cosmic ray patterns to historical shifts in Earth's climate, including small ice ages. If the flux outside our solar system is rising, and the bubble protecting us is being squeezed thinner, the consequences on Earth are real. Satellite electronics get fried. Airline crews on polar routes absorb higher doses. Astronauts on long missions face greater cancer risk. Voyager is measuring the storm we cannot feel yet. And the storm has a direction. When mission scientists mapped where the strongest cosmic rays were coming from, they drew lines backward into space. The lines converged. They pointed toward a region of sky that should have been empty. It was not empty. Something was sitting there. Something that seemed to be tilting the sun's entire magnetic bubble like a hand pressing on a ball. The sun's magnetic field is supposed to be symmetrical. For decades, scientists assumed the giant bubble of plasma and magnetism surrounding our solar system would be shaped roughly like a comet, round in the front where it plows through interstellar gas, stretched into a tail behind, simple, predictable, a perfect teardrop drifting through the galaxy. Voyager proved that picture wrong. Both Voyager 1 and Voyager 2 crossed the heliopause. When scientists compared the angles at which each probe exited, the numbers did not line up the way they should. The magnetic field on the inside of the bubble was tilted. The field on the outside was tilted too, but in a different direction. The two fields met at an angle no model had accounted for. Our sun's protective shield is leaning. Imagine holding a beach ball in a strong wind. If the wind blows perfectly from one direction, the ball stays centered. If a second wind comes in from the side, the ball tilts. The sun's bubble is doing the second thing. Something is pushing on it from an angle. Scientists traced the tilt and looked for a cause. The most obvious suspect was the interstellar magnetic field itself, the background magnetism of the galaxy that fills the space between stars. That field is not uniform. It has its own direction, its own strength, its own local weather. When our solar system moves through it, the bubble gets pressed against it like a ship leaning into a current. The interstellar magnetic field in our area is angled about 30 degrees off from what textbooks once assumed. That angle matches the tilt Voyager measured on its way out. Case closed, maybe. Except for one problem. The tilt is not staying constant. Long-term Voyager data suggests the angle shifts slightly over years. The bubble is flexing, wobbling, responding to changes in whatever is pressing on it from outside. Scientists have a few guesses. One is that our solar system is moving into a region with a stronger magnetic field. Another is that the field itself has knots and pockets, and we are drifting through them the way a car passes through patches of fog on a highway. The consequences of the tilt are strange. The bubble is now believed to be asymmetric, thicker on one side, thinner on the other, stretched longer in some directions than others. Cosmic rays leak in more easily through the thin areas. Solar particles escape more freely through the fat ones. The whole system is lopsided. A tilted shield is a compromised shield. Here is where it gets stranger for us. Earth orbits inside this bubble. The planet's own magnetic field is a much smaller version of the same idea, protecting us from radiation. When the sun's bubble leans, the pattern of cosmic rays reaching Earth changes. Some regions get more, some get less. Over decades, these shifts can influence how much radiation hits our upper atmosphere, how satellites age, and how often auroras appear at unusual latitudes. Voyager gave us the first real measurement of this tilt. Without the probe, we would still be drawing that symmetric teardrop in textbooks. Instead, we now know our home is wrapped in a bubble that leans, flexes, and reacts to forces beyond our star's control. The lean is part of a larger deformation. The bubble is not just tilted, it is being crushed into a shape nobody expected. For most of the space age, the heliosphere was drawn as a teardrop, a round head, a long tail, moving through the galaxy like a cosmic comet. That image appeared in textbooks, museum exhibits, and every NASA poster for 4 decades. Then new data arrived from a small spacecraft orbiting Earth called the Interstellar Boundary Explorer, nicknamed IBEX, and the teardrop fell apart. IBEX does something clever. It cannot travel to the edge of the solar system, so instead it catches particles that bounce off the heliopause and fly back toward Earth. By mapping where those particles come from, scientists can sketch the shape of the bubble from the inside. It is like using echoes to draw the walls of a cave. The first maps came out around 2010. They showed something impossible. The bubble was not a teardrop. It had no long tail. Instead, it looked compressed, rounded in weird places, flattened in others. When researchers combined IBEX data with Voyager measurements, the shape that emerged looked less like a comet and more like a crescent or a croissant. Two rounded lobes with a pinched middle, bending slightly as it moved. Scientists were stunned. A tail is a basic feature of anything moving through a fluid. Fish have them, comets have them, even bullets leave trails of disturbed air behind them. The sun's bubble should have had one too. Instead, the solar wind appeared to be looping back on itself near the rear of the heliosphere, caught in the galactic magnetic field and folded inward. Picture squeezing a water balloon between two hands. The balloon does not just shrink, it bulges at the top and bottom while being pinched in the middle. The heliosphere is doing something similar, except the hands squeezing it are made of interstellar plasma and cold galactic magnetism. The compression is uneven. The front, where the solar system plows forward, is thicker and denser. The sides are thinner. The back, instead of flowing into a long tail, collapses into a pocket where solar particles get trapped and bounce around for years before escaping. That matters because the croissant shape is not stable. As the sun's activity rises and falls through its 11-year cycle, the bubble inflates and deflates. During strong solar activity, the heliosphere pushes outward, fattening the front and stretching the lobes. During quiet periods, the bubble shrinks. The exact boundary where Voyager crossed moves inward and outward by hundreds of millions of miles over a solar cycle. This breathing motion has a consequence. A shrinking heliosphere means a thinner shield. During quiet solar years, more galactic cosmic rays reach the inner planets. Mission planners for future deep space crews now have to account for this. A trip to Mars during a solar minimum carries more radiation exposure than one during a maximum. Earth is tucked deep inside the bubble, but we still feel the shape. Seasonal cosmic ray patterns, satellite anomalies, small fluctuations in upper atmosphere chemistry, all trace back in part to the breathing of this croissant. When Voyager sent back pressure readings from the outer edge, it was measuring one hand of the squeeze. The other hand was still invisible. Scientists suspected something massive and unseen had to be pushing on the bubble from outside to produce a shape this warped. The answer came from a wind nobody could see. There is a wind blowing through our solar system that your eyes will never detect. It is called the interstellar wind. It is made of hydrogen and helium atoms, neutral and uncharged, drifting between the stars at roughly 52,000 miles per hour. From Earth, you cannot feel it. You cannot see it. You cannot measure it with any instrument on the ground. But it is there, every second of your life, streaming past our planet from a specific direction in the sky. That direction is the constellation Ophiuchus. Our entire solar system is falling through this wind as we orbit the center of the galaxy. The sun carries Earth and every planet along with it, plowing through the thin gas of interstellar space at tremendous speed. The wind pushes back. It shapes the front of the heliosphere. It compresses the bubble into its odd croissant form, and it carries atoms directly into our solar system, where spacecraft like Voyager and IBEX can finally catch them. For years, scientists assumed the direction of this wind was fixed. That assumption was wrong. In 2013, a team of researchers compared data from 6 different spacecraft spread across 4 decades. They found that the direction of the interstellar wind had shifted by 4 to 6 degrees over 40 years. That may sound small. It is not. Shifting the direction of an entire galactic breeze by several degrees in a human lifetime is like noticing that the jet stream over North America has flipped in the span of a single career. Imagine standing in a field where the wind has always blown from the west. One day you notice the grass bending slightly northwest. The next year it bends more. The wind is rotating. You cannot see what is causing it, but something upstream has changed. That is what the data shows. Scientists are not sure what is producing the shift. One theory is that our solar system is passing through a region of interstellar turbulence, pockets of gas with different densities and motions. Another theory is that the local magnetic field is twisting the flow of neutral atoms as they approach the heliosphere, and the twist itself is changing over time. Whatever the cause, the shifting wind has consequences. The interstellar wind determines which side of the heliosphere gets hit hardest. A change in direction means the compressed front of the bubble is now pointing slightly differently in the sky. Cosmic ray leakage changes. The thin spots in the shield move. The distribution of incoming particles to Earth's upper atmosphere shifts as well. Voyager measured this change firsthand. As it traveled outward, the relative flow of particles around it did not match predictions made from data taken when it launched in 1977. The wind had turned, and the wind is strong. Recent measurements suggest the pressure it exerts on the heliosphere is higher than models from the 1990s estimated. Our bubble is being pressed against a moving galactic river, and the river is changing course. Scientists now want to know what lies upstream, what kind of gas the wind is carrying, what temperature, what density. Because the solar system is not sitting still, it is moving, and the neighborhood we are drifting into matters far more than the one we are leaving behind. The first clue came from a cloud that surrounds us right now. Our solar system sits inside a cloud. It is not a cloud like the ones floating in Earth's sky. It is a vast, thin stretch of warm gas about 30 light-years across, filled mostly with hydrogen atoms. Scientists call it the local interstellar cloud, sometimes nicknamed the local fluff. The Sun entered it about 60,000 years ago. That is when our ancestors were still early hunter-gatherers sharpening stone tools. The cloud is warm, by interstellar standards, about 15,000 degrees Fahrenheit. It sounds terrifying until you learn how thin it is. There are only about a quarter of an atom per cubic centimeter of space. You could walk through it forever and never touch enough material to notice. But multiply that across trillions of miles, and the presence of the cloud becomes real. It pushes on our heliosphere. It feeds particles into our solar system. It shapes the environment Voyager is measuring. Here is the unsettling part. We are leaving it. The Sun is moving at about 50,000 miles per hour relative to the cloud, and projections from multiple research teams suggest we will exit it within the next few thousand years. Some models put the exit as soon as the next millennium. Others stretch it out to 50,000 years. The exact timing is a theory, not a confirmed fact. But the direction is clear. We are heading for the edge. Picture a small boat drifting across a lake of warm fog. The boat has been inside the fog for hours, but ahead, the fog thins. Beyond it lies another lake, different in temperature, different in color, different in the things it carries. Our solar system is that boat. The edge of the cloud is coming. Why does this matter? Because the cloud we are inside helps determine the size and pressure of the heliosphere. The thin gas of the local interstellar cloud pushes on our bubble from outside, balancing against the solar wind pushing out. When we exit the cloud, the outside pressure will change. If the next region is less dense, the heliosphere could expand dramatically, swelling outward like a balloon released into thinner air. If the next region is denser, the bubble could be squeezed smaller, pushing the boundary inward toward the planets. Either way, the conditions inside our solar system would shift. Cosmic ray exposure for Earth would change. The amount of interstellar dust reaching the inner planets would change. The neutral atoms feeding into Voyager-like measurements would come from a completely new source. There is more. The cloud we sit in has its own magnetic field, tilted at an angle scientists have only recently mapped with precision. That tilt is part of what deforms the heliosphere into its croissant shape. A new cloud means a new magnetic environment. The bubble would have to adjust. The tilt would change. The shape would change. And the local interstellar cloud is not alone. Around it, scientists have identified neighboring clouds with different properties, different densities, different chemistries, different magnetic signatures. The Sun is drifting from one into the next, and the map of what lies ahead has only begun to fill in. The next cloud on our path has already been located. It is hotter, it is denser, and it is waiting. Beyond the local interstellar cloud, the map shows something our solar system has never felt. It is called the G cloud. It sits in the direction of the constellations Centaurus and Scorpius. Our nearest stellar neighbor, Alpha Centauri, already drifts inside it. The G cloud is hotter than the cloud we are in now, with temperatures closer to 18,000 degrees Fahrenheit. It is also denser, containing more atoms per cubic centimeter than our current surroundings. When the Sun crosses the boundary between the two clouds, the environment around our solar system will change in ways that have not happened in tens of thousands of years. The timing is still uncertain. Some models suggest the crossing could happen within 2,000 years. Others push the estimate out to 15,000. The uncertainty comes from not knowing exactly where the cloud boundaries lie. Interstellar clouds are not sharp walls. They fade and overlap, and the Sun may actually be straddling the edge right now, with parts of the heliosphere already dipping into G-cloud material, while the rest still sits in the local fluff. Picture walking from a cool room into a warm, crowded one. At first, the change is subtle. A little more heat, a little more pressure from the bodies around you. Step deeper in, and the air thickens, the temperature climbs, the noise rises. Our solar system is in the doorway. The consequences are real. A denser cloud pushes harder on the heliosphere. The bubble would compress. The boundary Voyager crossed at 11 billion miles out might move inward by billions of miles, possibly shrinking the shield around the outer planets. Pluto, Neptune, even Uranus could find themselves closer to interstellar conditions than they are today. Cosmic ray flux at Earth would rise. Satellite operators would see more disruptions. Polar radiation doses for airline crews would climb. A hotter cloud also means more energetic atoms hitting the heliosphere. The interstellar wind would be faster, more aggressive, carrying more momentum into the outer solar system. Scientists estimate the solar wind's protective balance could weaken enough that the bubble might temporarily collapse inward in pulses, allowing bursts of interstellar material to wash over the planets. Theories about past cloud crossings suggest this may have happened before. Evidence buried in deep ocean sediments shows spikes of an unusual isotope called iron-60, which forms in supernova explosions. The spikes line up with moments when Earth may have passed through denser clouds. Some researchers believe those crossings corresponded with shifts in climate and biology. This is not confirmed. It is a hypothesis, actively debated, but the fingerprint is suggestive. The G-cloud carries more than heat and pressure. It carries its own magnetic field. That field has a different direction from the one our current cloud provides. When the Sun crosses over, the external magnetic environment will rotate, and the tilt of our heliosphere will shift with it. Auroras on Earth could change their patterns. The pathways that cosmic rays take into our inner solar system would rearrange. For now, Voyager is the only eyewitness close to the transition. Its plasma readings hint that the outer gas is already mixing. The boundary is not clean. There is something else Voyager is recording from inside the G-cloud's incoming pressure. A sound, a vibration, a plasma wave moving through interstellar space itself. Our Sun is not standing still. Right now, as you hear these words, the Sun is carrying Earth and every planet around it at roughly 450,000 miles per hour through the Milky Way galaxy. That is 7,500 miles every minute, more than 125 miles every second. You are hurtling through the galaxy on a planet strapped to a star, and nothing on your skin can feel it. We move as a group. The Sun pulls Mercury, Venus, Earth, Mars, all the gas giants, the asteroid belt, the Kuiper belt, and the enormous cloud of comets beyond, all dragged together through interstellar space like a convoy of trucks on a cosmic highway. The direction matters. The Sun is heading toward a point in the sky near the star Vega, in the constellation Lyra. Astronomers call this the solar apex. On the opposite side of the sky, the direction we are leaving behind is called the solar antepex. Everything the solar system encounters, it encounters first at the apex side. That is where the interstellar wind hits hardest. That is where the heliosphere is most compressed. That is the prow of our ship. Imagine a speedboat crossing a lake at night. Water splashes highest at the front. The wake stretches behind. Birds and floating debris appear first at the bow. The apex is our bow. Vega sits in the distance like a dim lighthouse, and we are charging toward it. Our speed is not unusual for stars in this region of the galaxy, But it is not random either. The Sun moves through what astronomers call the local standard of rest, which is the average motion of stars in our galactic neighborhood. We move relative to that average by about 43,000 miles per hour. That relative motion is what carries us into new clouds, new magnetic environments, new cosmic weather. Here is why it matters now. A slow star drifts gently through interstellar space. It spends a long time in each region, giving its heliosphere time to adjust. A fast star, like the Sun, punches through clouds more aggressively. Every few tens of thousands of years, it enters something new. The faster the star, the sharper the transitions. Our speed guarantees that we are always changing neighborhoods, and the changes are happening on timescales that matter for planetary conditions. Voyager has been measuring this motion directly. The probe's interaction with the interstellar medium depends on how fast the solar system is moving through it. The pressure on the heliopause, the angle of the incoming wind, the concentration of neutral atoms drifting into the inner solar system, all of it is a function of our velocity. If the Sun was slower, the bubble would be rounder, more symmetrical, less compressed at the front. If it were faster, the bubble would stretch and thin, with a sharper shock at the prow. Our current speed gives us the lopsided, tilted, breathing croissant Voyager is now exploring from the outside. Something else has shown up in Voyager's data stream from beyond the heliopause, a signal that does not match any known source, a slow, steady hum carried through the interstellar medium itself. Scientists called it a plasma wave, and it should not exist where Voyager heard it. Voyager 1 heard a sound in the dark. The probe has no microphone. Sound, as humans know, it cannot travel through the near vacuum of interstellar space. But Voyager carries an instrument that can detect vibrations in plasma, the electrically charged gas that fills the space between stars. When that plasma ripples, the instrument translates the ripples into signals that scientists can convert into audio. It is not sound in the traditional sense. It is the pulse of space itself. In 2012, shortly after crossing the heliopause, Voyager began detecting faint, steady plasma waves. They were weak. They were rare. Scientists picked up occasional bursts and logged them carefully. For years, that pattern held. Then, in 2017, the signal changed. The plasma waves became continuous. A low, persistent hum arriving from the interstellar medium around the probe. It did not fade. It did not spike. It simply kept going, month after month, a steady vibration riding through the gas beyond our solar system. That should not have been possible. Previous models of interstellar space assumed the plasma out there was too thin, too cold, and too still to produce a continuous wave. Scientists expected occasional disturbances triggered by bursts of solar activity or shockwaves from distant stars. They did not expect a constant tone. When the data came in, researchers at Cornell University who analyzed it were stunned. The interstellar medium, they realized, was not silent. Picture placing a stethoscope against the wall of a massive empty building. You expect nothing. Instead, you hear a steady, rhythmic hum, as if the building itself is breathing. You cannot find the source. You cannot trace the rhythm to any machine. But the hum is real, and it does not stop. That is what Voyager found. The hum carries information. Plasma waves reveal how dense the surrounding medium is. By studying the frequency of the waves, scientists could measure the density of interstellar gas at Voyager's exact location. The readings were higher than expected. The region around the probe has about 1/100th of an atom per cubic centimeter, which sounds tiny but is significantly denser than predictions for deep interstellar space. The higher density suggests we are still in a region shaped by the nearby cloud environment. The plasma is not empty, it is vibrating. It carries pressure waves that may be echoes of events far away. Old supernova shockwaves, motion of nearby stars, galactic-scale turbulence. Here is where the mystery deepens. Some of the wave patterns Voyager picks up do not match any obvious source. They arrive from directions that do not correlate with known solar activity, known shockwave fronts, or known nearby stellar events. Scientists have proposed theories: compressed gas pockets, magnetic reconnection events in the distant interstellar medium, even interactions with unknown structures in the galactic magnetic field. None of these are confirmed. They are working ideas, but the signal is real and it is consistent. The hum matters because it is the sound of our galactic neighborhood. For the first time in human history, a machine built by us is sitting in interstellar space and listening. What it hears changes our understanding of how the gas between stars actually behaves, and the hum is not the only strange signal in the sky. Around our solar system, IBEX discovered something even harder to explain: a narrow ribbon of energy circling the heliosphere, glowing in a direction nobody predicted. In 2009, the Interstellar Boundary Explorer sent back a map that should not have existed. The spacecraft was designed to sketch the outer edge of the heliosphere by catching atoms that bounce back from the boundary. Scientists expected a fairly smooth, even glow across the sky. Some bright regions, some dimmer ones, a soft haze of energy tracing the edge of our bubble. Instead, a bright, narrow strip of energy cut across the map like a brushstroke. It was not expected. It was not in any model. It was not predicted by any theory of how the heliosphere should interact with interstellar space. It was simply there, a glowing ribbon curving across the sky, hundreds of times brighter than the surrounding regions. Researchers named it the IBEX ribbon. The ribbon stretches in a long arc across the entire sky, wrapping around a portion of the heliosphere's outer edge. It is made of energetic neutral atoms, particles that were once charged, then neutralized during interactions at the boundary, then flung back toward Earth where IBEX could catch them. The brightness of the ribbon means something is generating an unusual concentration of these atoms in one specific curved region. Nothing in the textbooks explained why. Picture standing in a dark room holding a flashlight. You shine it on the walls and see a soft, even glow everywhere. Then you notice a single bright streak curving across the ceiling, as if someone painted it with glowing ink. The streak stays bright no matter how you turn. It is tied to the room, not to your flashlight. Something in the structure of the space itself is producing the glow. The ribbon is the same kind of mystery. Scientists have proposed several theories. The leading idea involves the interstellar magnetic field. As our heliosphere plows through interstellar space, charged particles bounce between the solar wind and the external magnetic field. In certain geometric alignments, those particles get trapped, neutralized, and re-emitted preferentially back toward Earth. The geometry creates a band, because only specific angles produce the effect. That theory explains part of the ribbon. It does not explain all of it. Some regions of the ribbon glow brighter than the geometry alone predicts. Some show changes over time that should not occur on short timescales. The ribbon appears to pulse, brighten, and dim in sections, in ways that scientists are still working to match against models. Voyager crossed through a part of the heliopause that sits near the ribbon's region. The probe's magnetic field readings from that area helped confirm that the interstellar field there aligns in the way the ribbon theories require. That was a win for the models, but it also deepened the mystery, because the alignment works only in the direction Voyager measured, and that alignment is not the same everywhere. The ribbon is a fingerprint of the interaction between our sun's bubble and the galaxy. It tells us where the magnetic field lines converge, where they diverge, where the pressure balance tilts one way or the other. It is a map, but the map is still being read. And the ribbon matters for another reason. It may be evidence that the galaxy itself is shaping our little bubble in ways we have only started to understand. The magnetic river, beyond the heliopause, does not just flow, it pushes. And pushing inward with it, something else. A gravitational tug reaching the most distant objects our solar system holds. Far beyond Pluto, far beyond the Kuiper belt, a vast shell of icy bodies surrounds our Sunday. It is called the Oort cloud. It is not a disk. It is a sphere, possibly trillions of comets wide, stretching from a few thousand astronomical units out to nearly a light year away. At that distance, the sun looks like a bright star. The Oort cloud objects drift in the cold, sluggish dark, barely held together by the sun's faint pull. No spacecraft has ever reached it. Voyager 1, the farthest human object in history, is still thousands of years away from entering the inner Oort cloud, even at its tremendous speed. We have never photographed it. We have never directly measured it. Everything we know about the Oort cloud comes from inference, calculation, and the occasional comet that falls inward from its depths. Here is the unsettling part. The Oort cloud appears to be getting tugged. Long-period comets, the ones that fall toward the Sun from the Oort cloud, arrive from specific directions in the sky. Over decades of tracking their orbits, astronomers have built a statistical map of where they come from. The map is not uniform. Some directions produce more comets, others produce fewer, and the imbalance shifts over time in ways that suggest gravitational disturbances deep in the cloud. Something is pulling comets loose. The Sun holds the cloud together, but only barely. At such extreme distances, the Sun's gravity is weak. Any passing object with enough mass, any galactic gravitational field, any nearby star drift, can nudge an Oort cloud comet out of its slow orbit and send it plummeting inward. That is how most long-period comets begin their journey. Something far away gives them a push. Picture a field full of soap bubbles floating in still air. Each bubble barely moves on its own. Now imagine a car passes nearby. The wash of air from the car disturbs the bubbles. Some drift one way, some pop, some get pulled toward the car's wake. The Oort cloud is the field. Passing stars and galactic tides are the car. The galactic tide itself is a real and measurable force. It is the gravitational pull of the entire Milky Way, summed up, acting on objects at extreme distances from the Sunday. Closer in, the Sun's gravity dominates. Out in the Oort cloud, the tide competes. Comets feel a tug toward the plane of the galaxy, a stretching along specific axes, a slow reshaping of their orbits over millions of years. Voyager's measurements matter here. The magnetic and pressure data from beyond the heliopause give scientists better numbers for how the interstellar environment interacts with our solar system. Those numbers feed into models of how the galactic tide acts on the Oort cloud. Better boundary conditions mean better predictions of how many comets should fall inward and from which directions. Recent statistical work on comet orbits has raised a question. The number of long-period comets arriving in certain directions seems higher than the baseline galactic tide alone would predict. Some researchers have proposed that a recent stellar flyby disturbed the cloud. Others suggest an unseen object deep in the outer solar system is adding its own pull. The Oort cloud is our early warning system. It feels changes before we do, and in recorded history, at least one star came close enough to reach through it. Stars are supposed to keep their distance. In the vastness of the galaxy, the average separation between stars is a few light years. Our nearest neighbor, Proxima Centauri, sits about 4¼ light years away. At that distance, even the largest stars look like faint points of light. Collisions between stars are almost unheard of. Near passes, however, happen more often than people realize. Scientists using precise data from the Gaia Space Telescope have reconstructed the paths of nearby stars over millions of years. The data is stunning. By tracking the positions, velocities, and trajectories of thousands of stars, astronomers can wind the galactic clock forward and backward. They can figure out which stars have come close to our solar system and which ones will in the future. The results have rewritten our view of the Sun's neighborhood. Over the past few million years, multiple stars have passed within a few light years of the Sunday. Some came closer than Proxima Centauri sits today. Each of these flybys, even from stars that look tiny and dim, carries enough gravitational influence to disturb the Oort cloud. A single passing star can nudge comets out of their slow orbits, sending some inward toward the inner solar system and throwing others out into interstellar space entirely. Picture a boat floating in a quiet lake. Another boat passes 100 yards away, not touching it, not hitting it. The wake still arrives. The first boat rocks. Ripples spread. That is a stellar flyby in slow motion, except the ripples are gravitational and the wakes last for millions of years. The flybys matter for Earth. When the Oort cloud gets disturbed, long-period comets begin falling inward over the following millions of years. Some eventually reach the inner planets. A disturbed Oort cloud means a higher comet flux. A higher comet flux means a higher risk of impacts. The geological record on Earth shows clusters of impact events that some researchers have tried to correlate with past stellar flybys, though the connection remains debated. Voyager's data helps anchor these models. The boundary conditions of our solar system, the pressure and magnetism Voyager measures at the heliopause, contribute to understanding how external forces propagate inward. A more accurate map of what is happening at the edge helps calibrate models of what happens even farther out. Some of the flyby candidates are surprising. A few of them are not bright, famous stars. They are dim, low-mass red dwarfs, hard to spot, easy to miss in earlier surveys. Others are binary systems, pairs of stars traveling together, whose combined gravitational influence doubles the impact on the Oort cloud. Gaia has identified dozens of candidate close encounters over the past 10 million years alone, most passed at distances of several light-years, enough to leave small imprints. A handful appear to have come closer. There is one flyby in particular that stands out. It happened recently, at least in cosmic terms. 70,000 years ago, while modern humans were already walking the Earth, a small star and its companion passed close enough to our Sun that they may have physically entered the outer Oort cloud itself. The star had a name, and when the numbers were run, astronomers realized it had reached into our neighborhood, stirred the comets, and left behind a wake we may still be feeling today. The star was small. The star was dim. The star almost went unnoticed. In 2013, astronomer Ralph Dieter Schultz identified a faint red dwarf in the constellation Monoceros. Paired with a brown dwarf companion, the system sat at an unremarkable distance. Its brightness was nothing special. Its spectrum was quiet. By every visible metric, it looked like one more dim object in a crowded sky. Then someone ran the numbers on its motion. The system was moving in an unusual way. Tangential velocity, the sideways drift across the sky, was almost zero. But its radial velocity, the speed at which it moved toward or away from us, was enormous. The star was heading directly away from the Sun at high speed, which meant, once the math was reversed, it had been heading directly toward us in the past. Running the trajectory backward, astronomers hit a wall. About 70,000 years ago, Schultz's star passed within roughly 0.85 light-years of the Sunday. To put that number in perspective, Proxima Centauri sits at 4.25 light-years. Schultz's star came 5 times closer than our nearest current neighbor. It crossed directly through the outer Oort cloud. A star passed through our comet shell while humans were already painting caves. Picture a truck speeding past a fragile web of bubbles. The truck does not hit the web directly, but its wake disturbs the strands. Bubbles shift. Some get pulled loose. Others spin into new positions. Schultz's star is the truck. The Oort cloud is the web. The disturbance is still playing out, because comets perturbed by that flyby travel on orbits measured in millions of years. The encounter is confirmed. The date, the distance, and the trajectory have been independently verified using different instruments and different stellar motion catalogs. The flyby is a fact. The consequences are where the theories begin. Scientists estimate that Schultz's star's passage through the outer Oort cloud could have nudged a significant number of comets onto new trajectories. Some would have been sent outward into interstellar space forever. Others would have been sent inward, falling slowly toward the inner solar system. The inward falling ones take a long time to arrive. Orbits from the outer Oort cloud can span millions of years, which means the reign of comets from Schultz's flyby has not yet reached us. Researchers have calculated rough timelines. Comets disturbed by the encounter would start arriving in the inner solar system hundreds of thousands to millions of years after the flyby itself. That window is open now. Some of the long-period comets astronomers have observed in recent decades may already be early arrivals from the Schultz wake. Confirming any specific comet as a direct result of the flyby is difficult, because Oort cloud comets take so long to arrive that their origin directions get scrambled by galactic tides along the way. Voyager's work at the heliopause contributes here too. Better boundary models mean better understanding of how incoming comets interact with the solar wind as they approach. The heliosphere affects how comet tails form, how volatiles sublimate, how the visible display appears in Earth's sky. Schultz's star was small. It was dim. It still reached us. A larger star, is coming closer, and its arrival time has already been calculated. There is a star heading toward us. Its name is Gliese 710. It is currently about 62 light-years away, drifting quietly through the constellation Serpens Cauda. It is a small orange dwarf, about 60% the mass of our Sunday. From Earth, it looks unremarkable, a dim dot requiring a telescope to see clearly. Most people will never notice it. Astronomers cannot stop tracking it because the numbers are clear. Gliese 710 is going to hit the edge of our solar system. Using data from the Gaia Space Telescope, astronomers have calculated the star's trajectory with remarkable precision. In about 1.3 million years, Gliese 710 will pass within roughly 0.15 to 0.2 light-years of our Sunday. That is far closer than Schultz's star, far closer than any other known stellar encounter in the future record. Gliese 710 will not graze the outer Oort cloud. It will plow directly through the heart of it. 1.3 million years sounds like forever. In galactic terms, it is tomorrow. Picture a slow-motion collision in deep space. A star, carrying its own planets or remnants, drifting on a direct course into a cloud of icy bodies that surrounds our Sunday. The cloud does not care about the star's intentions. The gravitational disturbance simply happens. When a stellar body of that size moves through the Oort cloud, it changes the orbits of millions of comets. Some fly outward and escape. Some fall inward toward the Sunday. The inward falling ones will take another round of hundreds of thousands to millions of years to reach the inner solar system. By the time the comet rain from Gliese 710 arrives, the human species as we know it may no longer exist. But if any descendants or inheritors of Earth are still around, they will witness a period with far more bright comets streaking through the sky than any time in recorded history. The details are as precise as modern astronomy allows. The flyby distance is a theory based on Gaia's measurements, which are the best data ever collected on stellar motion. The uncertainty is small, but real. The star could come slightly closer, or slightly farther. Either way, the penetration of the Oort cloud is a near certainty. This is not science fiction. It is calculated fact, published in peer-reviewed journals, refined with each new Gaia data release. Why does it matter now? Because the event shapes how we think about the long-term stability of our solar system. The Oort cloud, which seems distant and disconnected, is actually a dynamic region that responds to the galactic environment. Stars come, stars go, each one leaves a fingerprint. The solar system is not a sealed, isolated machine. It is an open system, exchanging material and energy with its surroundings on long timescales. Voyager is the first probe to measure the outer shell of that open system. The heliopause data, the plasma wave measurements, the cosmic ray flux, all of it contributes to a clearer picture of how our bubble interacts with its surroundings. When Gliese 710 eventually arrives, models built partly from Voyager data will predict how the event unfolds. For now, the star drifts on, silent, patient, aimed at us, and the galaxy itself is adding its own pull to the long, slow reshaping of our neighborhood. Gravity does not stop at the edge of our solar system. The entire mass of the Milky Way, billions of stars, oceans of dust, veins of dark matter, all of it exerts a pull on every object orbiting our Sunday. Close to the Sun, the pull is negligible. The Sun dominates. The planets orbit in neat patterns. Earth, Mars, Jupiter, all firmly locked in their paths. But at the fringes of the solar system, where the Sun's grip weakens, the galaxy starts to matter. This long-range pull is called the galactic tide. The galactic tide is not a single force pointing in one direction. It is a gradient, a stretching and compressing that varies with position in the galaxy. Imagine standing on a beach while the tide comes in. The water rises on all sides, but it rises unevenly. Low spots fill first. High ground stays dry longer. The shape of the land determines how the water flows. In the galaxy, the shape of the gravitational field determines how loose objects in the Oort cloud get pulled. Objects in the outer Oort cloud feel the tide more strongly than objects closer in. The Sun's gravity falls off with distance. The galactic tide does not fall off in the same way. At about 100,000 astronomical units from the Sun, the two forces become comparable. Beyond that, the galactic tide starts to win. That threshold is where the Oort cloud becomes unstable on long timescales. Here is the mechanism. A comet in the outer Oort cloud orbits slowly, taking millions of years to complete a single loop around the Sunday. During that loop, the galactic tide gently stretches and twists the orbit. Over many cycles, the stretching adds up. Some comets get their perihelia, their closest approach to the Sun, pulled inward. Once inside a certain distance, Jupiter and the other giant planets can take over and scatter the comets onto new paths. Some fall into the inner solar system, some get flung into interstellar space. Voyager's measurements of the heliopause environment feed into models of how the galactic tide interacts with the solar system's outer boundary. A more accurate map of the bubble's shape, the external pressure, and the local magnetic environment helps refine estimates of how fast the tide is reshaping the Oort cloud. The tide also has a direction. It pulls more strongly along certain axes than others, especially perpendicular to the galactic plane. Comets feel the pull most when their orbits are aligned in certain ways. This creates a statistical signature in the arrival directions of long-period comets. Over decades of comet tracking, the signature has been detected. It matches theoretical predictions. The galactic tide is real, measurable, and constantly at work. Some researchers believe the tide is not entirely constant. As the Sun moves through the galaxy, the local density of matter changes. Passing through dense regions, like spiral arms or dense molecular clouds, strengthens the tide temporarily. Passing through thinner regions weakens it. Our solar system experiences waves of stronger and weaker tidal influence over millions of years. The tide bends, stretches, and reshapes the outer reaches of our solar system. It is one of the forces Voyager's data helps us understand from the inside out. But something else may be hiding out there. A body large enough to tug on the orbits of the farthest known objects in our solar system, and Voyager's measurements may have just strengthened the case. Some of the most distant objects in our solar system are behaving strangely, beyond Neptune, beyond Pluto, out in the cold, sparse region called the Kuiper Belt and the scattered disk. Astronomers have found a cluster of small, icy worlds whose orbits do not look random. Their paths are tilted, they are stretched, and their long axes seem to point in similar directions in space, as if being herded together by something massive. This is the core of the Planet 9 hypothesis. In 2016, Caltech astronomers Konstantin Batygin and Mike Brown published a paper arguing that the clustering of distant trans-Neptunian objects was not a coincidence. The pattern, they said, was best explained by the gravitational influence of a large undiscovered planet in the outer solar system. They estimated its mass at roughly 5 to 10 times that of Earth, orbiting at an average distance of several hundred astronomical units, possibly as far as 1,000. Planet 9 would not be a gas giant like Jupiter. It would more likely be a Neptune-sized world, cold, dark, and very distant. Its sunlight exposure would be minimal. Its surface temperature would be close to absolute zero. Finding it would require searching faint, moving dots in regions of sky where the galactic background is crowded with stars. The search has been ongoing for years. Telescopes have swept wide areas of the sky. Some candidate regions have been ruled out. Others remain unexplored. Planet 9 has not been directly detected. It remains a hypothesis, actively debated in the astronomical community. Some researchers argue the orbital clustering could be explained by observational bias. The more objects found, the more the pattern might fade. Others argue the clustering is real and strong enough that a perturber is required. The debate continues. Voyager's data contributes to the conversation in an unexpected way. The probe's measurements of the heliopause environment give scientists cleaner models of the outer solar system's boundary conditions. Those models feed into simulations of how distant objects move under the combined influence of the Sun, the galactic tide, passing stars, and any possible unseen planet. Better boundary conditions reduce noise in the simulations. Picture trying to find a ghost by watching how furniture rearranges itself at night. You need to rule out every other cause first: the wind, the cat, the house settling. Only when you have clean data on everything else can you say with confidence that something unseen is doing the moving. Voyager helps rule out other causes at the edges of the solar system. Recent analysis using updated boundary data has, according to some researchers, strengthened the case that known forces alone cannot fully explain the orbital clustering. This is a theory, not a confirmed result. Other teams have reached different conclusions with different assumptions. The evidence is suggestive. It is not final. If Planet 9 exists, it would reshape our understanding of how our solar system formed. A large planet that did not originate there. It was likely scattered outward during the chaotic early history of the solar system, or possibly captured from another star during a close flyby. Either way, its existence would tell us that our planetary family has more members than we realized. Voyager cannot see Planet 9. The probe is nowhere near the right region of sky, but the data it sends back sharpens the tools we use to look. And Planet 9 is not the only unexplained motion in the outer solar system. Something was already pulling on spacecraft before Voyager reached the edge. Before Voyager, there was Pioneer. Pioneer 10 and Pioneer 11 launched in the early 1970s. They were the first probes sent on trajectories that would carry them beyond the planets. They flew past Jupiter. Pioneer 11 went on to visit Saturn. Then both spacecraft kept going, drifting outward into the darkness, quietly sending back data for decades. Somewhere along the way, they started drifting in a way nobody expected. Navigators at the Jet Propulsion Laboratory tracked the probes using radio signals. By measuring tiny shifts in the frequency of the returning transmissions, they could calculate each spacecraft's speed with astonishing precision. The math should have been simple. Gravity from the sun and planets determines the path. The probes should follow predicted trajectories to within a hair's width. They did not. Both Pioneer probes appeared to be slowing down slightly more than gravity alone predicted. The effect was tiny, a sunward acceleration of about 8.74 times 10 to the negative 10 meters per second squared. That number is almost incomprehensibly small. It would take 1 billion years of steady pull to make a noticeable dent in a planetary orbit. But across decades of high-precision tracking, the anomaly was real, consistent, and measurable. Scientists called it the Pioneer anomaly. For more than 20 years, nobody could explain it. Theories ran wild. Some suggested undiscovered matter in the outer solar system. Others proposed new physics, modifications to gravity at large scales, subtle failures of general relativity over long distances. A few papers floated ideas involving dark matter, exotic fields, or even errors in the established constants of nature. Picture a car rolling down a long, empty highway. You expect it to coast for a certain distance based on its momentum and the road's incline. It coasts slightly less. Every time, the car is fine. The road is flat. But something in the environment is adding a whisper of drag that you cannot see. That is what Pioneer was feeling. After years of analysis, the anomaly was eventually explained by thermal emission. The probes radiated heat unevenly. The side facing away from the sun was warmer than the side facing toward it because the radioisotope power sources and the electronics sat in specific locations. The uneven heat radiation produced a tiny thrust, pushing the spacecraft sunward. When that effect was carefully modeled, it accounted for most of the observed drift, but not all of it. A small residual remains. Some researchers consider it within measurement uncertainty. Others argue it points to something else still operating on the spacecraft. The debate is quieter now than it was 20 years ago, but it is not fully settled. Voyager has not shown the same anomaly at the same magnitude. Its engineering is different. Its heat radiation profile is different. But the lessons from Pioneer shaped how Voyager's navigation teams interpret their own tiny trajectory deviations. Every unexplained microshift gets scrutinized. Thermal models get run. Radio pressure gets checked. Solar wind drag gets calculated. The outer solar system is a precision environment. Tiny forces add up over billions of miles. Voyager's team has gotten very good at separating real physical effects from instrumental noise. And the probe is now in a region where those tiny forces include interactions with the interstellar medium itself. Somewhere in that medium, if some theories hold, invisible material may be flowing through our solar system right now, and a handful of physicists think they have already seen its shadow. Most of the matter in our galaxy does not give off light. It does not emit. It does not absorb. It does not glow in infrared, radio, ultraviolet, or any wavelength telescopes can detect. It is called dark matter, and it outweighs the visible matter in the Milky Way by roughly 5 to 1. It holds galaxies together, it shapes cosmic structure, and it is everywhere around us, passing through the Earth, through your body, through every second of your life. We have never directly detected a dark matter particle. We infer its existence from gravitational effects. Here is where things get interesting for our neighborhood. Dark matter does not sit still, it flows. As our solar system orbits the galactic center, we plow through dark matter just as we plow through the interstellar medium. Physicists estimate our planet passes through enormous quantities of dark matter every second. The density is low, but the volume is vast. Some of that dark matter may be organized into streams. When smaller galaxies get pulled apart by the Milky Way's gravity, they leave behind long trails of stars and dark matter stretched along their old orbits. These trails are called tidal streams. Several have been mapped using visible stars. Each star stream is presumed to have a dark matter component, traveling alongside it, invisible but coherent. A few of those streams appear to pass through our solar neighborhood. One of the most studied is associated with the Sagittarius dwarf galaxy, which has been torn apart over billions of years. Its debris stretches across much of the sky. Computer simulations suggest streams from this disruption may cross the region of the galaxy where our sun sits. If so, we are currently moving through a flow of dark matter with a specific direction and speed, possibly different from the average dark matter wind expected from our galactic motion alone. Picture standing in a river where most of the water flows smoothly in one direction. Then a faster current braids through the main flow, cutting diagonally across your position. You cannot see the current, but your instruments notice the difference. Dark matter streams would behave that way. For direct detection experiments, this matters. Laboratories buried deep underground try to catch dark matter particles as they collide with atomic nuclei. The expected signal depends on the speed and direction of incoming particles. If a stream is passing through Earth, the signal should have a distinct signature, a slight annual modulation, or an excess from specific directions in the sky. Some experiments have reported hints of such signals. Others have seen nothing. The field remains divided. This is a theory, still being tested. Voyager cannot detect dark matter directly. Its instruments are not sensitive to the faint gravitational whispers dark matter might produce. But the probe's work defining the boundary of our solar system contributes to the broader picture of how galactic influences reach us. Pressure from outside, magnetic fields from outside, possibly streams of invisible mass from outside. If dark matter streams do thread through our neighborhood, they add another force to the slow reshaping of the outer solar system. Over enormous timescales, subtle tugs from these streams could contribute to how the galactic tide acts on the Oort cloud. The effects are small. They are cumulative. The sun itself may be responding to these galactic pressures in ways we can measure more directly. And right now, our star is losing mass faster than scientists once thought. The sun is shrinking. It is not collapsing. It is not dying anytime soon. But every second of every day, our star sheds material into space, and the total mass it loses over time is larger than older estimates suggested. The loss happens through two main channels. One is the solar wind, the stream of charged particles constantly blowing outward from the sun's surface. The other is nuclear fusion itself, which converts hydrogen into helium and releases energy according to Einstein's famous equation, a small amount of mass becoming a large amount of radiation. The numbers are staggering. The sun converts about 4 million tons of mass into pure energy every second through fusion. That energy streams out as sunlight, warming Earth, driving weather, feeding plants. Another several million tons per second blow away as solar wind. Over the course of a year, the sun loses roughly 130 quadrillion tons of material. Compared to the sun's total mass, this is tiny. The sun has enough fuel to shine for billions of years. but the cumulative effect matters for understanding the long-term evolution of our star, and therefore the long-term evolution of our solar system. Here is what recent work suggests. Measurements from multiple spacecraft, including Voyager, Ulysses, and the Parker Solar Probe, indicate that the Sun's mass loss rate varies more than previously thought. During periods of high solar activity, the wind blows faster and denser. During quiet periods, it slows and thins. The long-term average appears slightly higher than estimates from the 1980s. Picture a campfire. Most of the time, it burns at a steady pace, sending up a column of smoke. Occasionally, a log shifts and the fire roars, throwing sparks and ash into the air. The Sun behaves similarly, with coronal mass ejections and solar flares spraying extra material outward during active periods. Over decades, those episodes add up. Voyager's long baseline has been essential. The probe has measured the solar wind for almost 50 years across multiple solar cycles. No other mission has tracked the outward flow for so long at such great distances. By comparing Voyager's in-situ measurements with data from closer spacecraft, scientists can map how the solar wind changes as it expands outward. Why does mass loss matter? A lighter sun exerts slightly less gravitational pull. Over billions of years, the shift is enough to change planetary orbits. The Earth is already drifting outward by a few centimeters per year as a result. The effect is tiny on human timescales. Over the lifetime of the Sun, it becomes significant. Mass loss also shapes the heliosphere. More wind means more outward pressure, which inflates the bubble. Less wind means the bubble shrinks. Voyager has directly observed the boundary of the heliosphere moving inward and outward over years as the Sun's output changes. The probe is sitting, right now, in a region whose distance from the Sun depends partly on how much material our star has shed recently. There is concern in the community about recent trends. Solar wind pressure measurements over the past few decades show an unusual pattern. The outflow is weakening, and nobody is entirely sure why. Something strange has been happening to the Sunday. Starting around the mid-1990s, measurements of the solar wind began showing a decline. The outward pressure of the wind dropped. The density of particles in the wind fell. The strength of the magnetic field embedded in the flow weakened. By the early 2000s, the values had reached lows not seen since spacecraft began tracking the wind in the 1960s. The trend stunned scientists. The solar wind had been considered stable on century timescales. Models assumed it fluctuated with the 11-year solar cycle, but returned to roughly the same averages across cycles. The new data said otherwise. The Sun appeared to be entering a quieter state. By the mid-2000s, the wind pressure was about 20% lower than the averages observed during the 1970s. That is a significant drop, enough to reshape the outer boundary of the heliosphere, enough to change the amount of cosmic radiation leaking into the inner solar system, enough to influence every spacecraft operating beyond Earth's atmosphere. Picture a garden hose running at full pressure. Water shoots out hard, pushes debris away, keeps the flower beds clear. Now imagine someone slowly turns down the faucet. The water still flows, but weakly. Leaves start collecting. Dust accumulates at the edges of the beds. The outer boundary of where the water can reach pulls inward. That is what happened to the solar wind. Voyager, drifting outward through all of this, recorded the consequences directly. The boundary of the heliosphere, the wall the probe eventually crossed, sat closer to the Sun than earlier models predicted. The bubble had shrunk. Interstellar cosmic rays flooded into the outer solar system in greater numbers. Voyager's cosmic ray detectors logged the highest fluxes ever measured during that period of low solar wind. There is debate about why the Sun weakened. Some researchers attribute the decline to a natural long-term oscillation in solar activity. The Sun has gone through extended quiet periods before. The most famous is the Maunder minimum, a stretch in the late 1600s when sunspot activity almost vanished. Europe experienced unusually cold winters. Some correlate it with the end of the Little Ice Age. The connection between solar minima and Earth's climate is debated, but the Sun itself was measurably different during that period. The current quiet phase has been called a grand solar minimum candidate by some researchers. Whether it reaches the depth of the Maunder minimum remains uncertain. Solar cycle 24. which ran from roughly 2008 to 2019, was the weakest in about a century. Cycle 25, which began in late 2019, has been running stronger but still below long-term averages. The implications are real. A weaker sun means a weaker heliosphere. A weaker heliosphere means more cosmic ray exposure for the planets inside it. Satellite electronics face higher radiation doses. Astronauts on long missions face elevated cancer risks. Polar airline routes see more radiation for crew members. Voyager's data captured the peak of the decline. As the probe approached and then crossed the heliopause, it measured the exact environment produced by a weakened Sunday. The boundary the spacecraft finally punched through sat at a distance, shaped in part by decades of dropping solar wind pressure. The quieting sun has consequences for the size of the bubble around us. The bubble is not just shrinking, it is changing Earth's exposure to what lies beyond it. A smaller heliosphere means a thinner shield. Every particle of the solar wind pushes outward against the interstellar medium. When the wind weakens, the interstellar medium pushes back harder, the boundary retreats, the bubble we live inside gets smaller, and the inner planets, including Earth, move closer to the zone where interstellar radiation begins to leak through. During the recent quiet phase of the Sun, the heliosphere shrank by billions of miles. The exact amount is estimated from models calibrated against Voyager data. The boundary at the time of Voyager 1's crossing sat at roughly 121 astronomical units. During a stronger solar cycle, it might sit at 140 or more. The difference is real. The location of the bubble's edge moves. For Earth, the consequences are measurable but subtle. Galactic cosmic rays, the high-energy particles coming from outside the solar system, arrive at Earth in greater numbers when the heliosphere is weak. During the recent solar minimum, cosmic ray fluxes at Earth reached the highest levels ever recorded by modern instrument. NASA's Advanced Composition Explorer, which sits at the L1 Lagrange point between Earth and the Sun, tracked the rising counts in real time. Picture a leaky roof. A good roof keeps almost all the rain out. A roof with a few worn patches lets water through in specific places. As the patches grow, more water gets in, and the damage accumulates. The heliosphere is our roof. The Sun's activity determines how many patches appear, what reaches Earth when the heliosphere weakens. Cosmic rays themselves are the biggest change. More high-energy protons, helium nuclei, and heavier ions hit the top of Earth's atmosphere. Most get absorbed by air molecules, producing cascades of secondary particles that eventually lose energy. A small fraction reach the ground. An even smaller fraction penetrate into human bodies, aircraft, and satellites. Satellite operators see the effect clearly. Single event upsets, sudden bit flips in memory, caused by a cosmic ray strike, become more common during quiet solar periods. Spacecraft mission planners account for this by hardening electronics, using redundant systems, and scheduling sensitive operations to avoid the worst conditions. Airline crews on polar routes absorb measurable extra radiation during quiet solar years. The atmosphere is thinner at high latitudes, and Earth's magnetic field funnels cosmic rays toward the poles. A pilot flying New York to Tokyo dozens of times per year can accumulate a noticeable dose. Regulatory agencies track this. Astronauts face even more exposure. On the International Space Station, crews already receive a radiation dose much higher than ground level. During cosmic ray peaks, that dose climbs further. For future missions to Mars, the risk of radiation exposure becomes a central planning challenge. A 3-year Mars mission during a weak solar period could push astronauts near or past allowed career radiation limits. Long-term climate effects are debated. Some researchers argue that increased cosmic rays during weak solar periods seed more cloud formation, which cools the planet slightly. Others argue the effect is too small to matter. The correlation between solar activity and past climate shifts remains an active area of research. It is not a settled question. Voyager's view from beyond the bubble gives the most direct measurement available of how the interstellar environment is pressing against us. And Voyager also sits inside a much larger structure we never knew we were part of. A cosmic bubble carved by ancient explosions, surrounding our entire neighborhood. Our entire solar system is floating inside a cavity. The cavity is called the local bubble. It is a roughly spherical region of hot, low-density gas, stretching about 1,000 light-years across, carved out of the interstellar medium by ancient supernova explosions. Inside the bubble, the gas is thin and hot, around 1,000,000 degrees Fahrenheit, but so diffuse that a spacecraft passing through it would feel nothing. Outside the bubble, the gas is cooler and denser, packed into walls of material that ring the cavity. The sun sits near the middle of the local bubble. Our whole journey through the galaxy for the past several million years has taken place inside this hot, hollow region. Astronomers have known about the local bubble for decades. What changed recently is the precision with which its boundaries have been mapped. In 2022, a team of researchers used data from the Gaia Space Telescope combined with dust maps to produce a three-dimensional model of the cavity. The model confirmed what earlier studies suggested. The bubble is real. Its walls are dense with gas and dust, and the young stars forming today on the bubble's surface sit exactly where the theory predicted they would. Picture blowing a soap bubble inside a mist-filled room. The bubble pushes the mist outward, creating a thin ring of condensed vapor around its edge. Inside the bubble, the air is clear. Outside, the mist returns. Supernovae blew the local bubble. The explosions pushed interstellar gas outward, sweeping it into a wall that now forms the cavity's boundary. How many supernovae did it take? Researchers estimate the local bubble formed from roughly 15 supernova explosions over the past 10 to 15 million years. The exploding stars belong to a stellar association that has since drifted apart, its surviving members now scattered across nearby constellations. The combined energy of those explosions carved out the cavity and heated the gas inside to its current state. Here is the important part. The local bubble is not static. It continues to expand slowly, and its walls are still moving outward. The young stars, forming on the bubble's surface, are being compressed by the shockwave that swept the material outward. Star formation in our part of the galaxy over the past few million years has been concentrated along the bubble's expanding edge. Voyager is now exploring the interstellar gas inside the bubble. The low-density, hot gas the probe measures beyond the heliopause is the interior of the cavity itself. The nearest wall of the bubble is still hundreds of light-years away in most directions, far beyond where any human-made object will reach for millennia. The discovery of our position inside the local bubble reshaped how astronomers think about the sun's environment. We are not drifting through generic interstellar space. We are inside a specific, shaped cavity whose properties were determined by ancient cosmic violence. The implications run deep. The chemistry of the gas around us, the density of cosmic rays, the shape of the heliosphere, all of it is partly determined by the fact that we live inside a supernova bubble. If we exit the bubble someday, the change will be dramatic. The sun would leave hot, thin gas and enter cooler, denser material. The heliosphere would compress. The environment for Earth would shift. Evidence suggests some of those ancient supernovae left a direct signature on our planet, and that signature has been buried in deep ocean mud for millions of years. There is a radioactive isotope at the bottom of the Pacific Ocean that should not be there. It is called iron-60. It is a form of iron produced almost exclusively in the extreme conditions of supernova explosions. Iron-60 is radioactive, decaying with a half-life of about 2.6 million years. Anything older than about 15 million years has long since decayed away to undetectable levels. Anything younger still carries a measurable signal. In the 1990s, researchers drilling into deep-sea sediments off the coast of South America found iron-60. They found it in specific layers. Dating those layers revealed something extraordinary. The iron-60 had been deposited on Earth between about 1.5 and 3 million years ago. Multiple supernova explosions had rained radioactive material onto our planet. Follow-up studies expanded the discovery. Iron-60 showed up in sediment cores from multiple oceans around the world. It showed up in ice cores from Antarctica. It even showed up in samples from the Moon, where material does not get weathered away as it does on Earth. The signal was global. The events were real. Picture a thin layer of cosmic dust, sprinkled across every ocean floor and every polar ice sheet, carrying the chemical fingerprint of ancient stars that exploded. The dust arrived slowly, over hundreds of thousands of years, as the solar system passed through the expanding debris fields of nearby supernovae. Scientists have tried to identify the source. The timing of the Iron 60 peaks correlates with the sun's passage through the local bubble's formation period. The explosions that carved the bubble likely also seeded Earth with their radioactive byproducts. Could one of those explosions have affected life on Earth? This is where theory enters. Some researchers have proposed that the supernovae, occurring within perhaps 300 light-years of Earth, may have increased cosmic ray flux at the surface. Higher cosmic rays could have affected cloud formation, climate patterns, and possibly evolutionary pressures on marine life. There are documented extinction events and climate shifts in the fossil record roughly aligned with the Iron 60 peaks. The connection is not proven. Correlation is not causation. But the timing is suggestive, and the Iron 60 itself is a hard fact. Voyager's measurements of the current interstellar environment give scientists a baseline for understanding how supernova material spreads through the local bubble. The probe is drifting through gas that includes, at some level, the remnants of those ancient explosions. The isotopic composition of the interstellar medium in our region carries the signatures of the supernovae that shaped our neighborhood. More Iron 60 is likely waiting in sediments we have not yet analyzed. As technology improves, researchers are finding Iron 60 in younger samples, suggesting the supernova material is still arriving today in tiny quantities. The dust cloud from explosions that happened millions of years ago is so vast that our solar system is still sweeping through the remnants. The local bubble is not the only large-scale structure shaping our neighborhood. Nearby, astronomers have found something even stranger, a massive, undulating wave of gas and stars curling through the sky that nobody knew existed until 2020. In 2020, astronomers announced the discovery of a structure that had been hiding in plain sight. They called it the Radcliffe wave. It is a vast, undulating ribbon of gas and young stars, stretching about 9,000 light-years across and passing through our galactic neighborhood. For decades, the various star-forming regions that make up the wave had been studied separately. Each was treated as its own object. Then, a team using precise Gaia data plotted their three-dimensional positions and realized something startling. They were all part of the same wave. The Radcliffe wave curls through space like a giant serpent, rising above and falling below the galactic plane in a long sinusoidal pattern. Our solar system sits close to it, perhaps within 500 light-years of its nearest segment. Many of the brightest and most familiar star-forming regions visible in Earth's sky, including parts of the Orion complex, lie along the wave. The structure was invisible until recently because of perspective. From the inside of the galaxy, looking along the wave, the objects blur together. Looking across the wave, they line up in ways that seem coincidental. Only a full three-dimensional map revealed the truth. Picture a long, rippling flag stretched across the sky. From some angles, it looks like a single line. From others, it looks like a pile of disconnected patches. Only when you can walk around it and see it from all sides do you notice that it is one continuous structure, waving in slow motion. The wave is not static, it is oscillating. Recent analysis suggests the Radcliffe wave is undulating over time, its stars and gas moving up and down through the galactic plane in a coordinated wave motion. The period of the oscillation is measured in tens of millions of years. Something set the wave in motion. The cause is still being studied. One theory involves an ancient galactic collision. When smaller galaxies or dense gas clouds pass through the Milky Way, they can set up wave-like disturbances in the disk. Another theory points to internal dynamics, perhaps the combined effect of supernovae and gravitational instabilities driving long-term oscillations in the gas distribution. These are theories. The data supports each partially. More work is needed. Our solar system may have passed through a segment of the wave in the past. As we orbit the galaxy, We rise and fall through the galactic plane ourselves, with a period of about 66 million years. Some researchers have attempted to correlate those passages with extinction events in Earth's fossil record, under the idea that denser regions carry more supernova risk or stronger cosmic ray exposure. The correlations are weak and contested. It remains an open question. The Radcliffe wave matters because it reshapes how we picture the Sun's neighborhood. The galaxy near us is not a flat, uniform disk of stars. It is structured, lumpy, and dynamic. Large waves of gas move through it. Young stars form preferentially in certain regions. Supernovae go off in clusters along the wave. The environment our solar system passes through varies from place to place and time to time. Voyager's measurements of the current interstellar medium give a snapshot of our position inside this larger structure. And the Sun itself is not staying in one place relative to the wave. Our star is climbing out of the galactic plane right now. The Milky Way is not a perfectly flat disk. It has a thickness. Most stars concentrate near a central plane, but individual stars bob up and down above and below this plane as they orbit the galactic center. The motion is a slow, gentle oscillation driven by the galaxy's gravity, pulling stars back toward the disk whenever they drift too far. The Sun is doing this right now. Astronomers have measured our star's current position and motion relative to the galactic plane. At present, the Sun sits about 60 light-years above the plane and is moving upward at around 4 miles per second relative to nearby stars. We are not at the peak of our oscillation yet. We are still climbing. Picture a ball on a stretched rubber sheet. The ball rolls forward, and as it rolls, it bounces gently up and down. The sheet pulls it back toward the center, but momentum carries it across. The ball traces a rolling wave pattern. Our Sun is the ball. The galactic plane is the sheet. The full oscillation takes about 66 million years from peak to peak. During that time, the Sun rises above the plane, reaches a maximum height of roughly 200 light-years, and falls back. Then it crosses through the plane and descends to a similar depth on the other side before rising again. Why does this matter? Because the environment varies with height above the plane. Near the plane, gas and dust concentrate. Supernova density is higher. Young star formation is more active. Cosmic ray flux tends to be greater. Away from the plane, the galaxy thins out. Fewer stars, less gas, lower radiation levels from nearby events. Some researchers have tried to correlate the Sun's vertical oscillation with patterns in Earth's geological history. A team proposed that crossings through the galactic plane might align with pulses of comet impacts as the Sun passes through denser regions where its Oort cloud gets disturbed. The idea is called the galactic tide hypothesis for impact cycles. The correlation is debated. Some statistical analyses support it, others do not. The galactic plane crossing hypothesis remains a theory, not a confirmed mechanism. What is confirmed is the motion itself. Gaia data has pinned down the Sun's vertical position and velocity with remarkable precision. We know where we are relative to the plane, and we know which way we are moving. Currently, upward. Our heliosphere reflects this motion to some degree. The interstellar wind direction, the local magnetic field orientation, the density of nearby gas, all vary with position in the galaxy. As we rise, these quantities shift. The measurements Voyager takes today are slightly different from what they would have been a million years ago, and slightly different again from what they will be a million years from now. The vertical oscillation also affects our position within the local bubble. The bubble is a roughly spherical cavity, but the Sun is currently offset from its center. As we move upward, we approach one of the bubble's walls more closely. Eventually, perhaps several million years from now, we may exit the bubble entirely through the northern wall. Exiting would mean leaving hot, thin gas and entering the cooler, denser interstellar medium beyond. And exiting would bring consequences we are only beginning to understand. Someday, the Sun will exit the local bubble. The timing is uncertain. The direction is clearer, based on the Sun's current vertical motion and the mapped geometry of the bubble. Our solar system is heading generally upward and outward toward one of the cavity's walls. The exit point is probably in the direction of certain northern constellations. The journey could take anywhere from a few million to tens of millions of years, depending on the sun's exact trajectory and how the bubble's boundaries shift. When we cross the wall, the environment around our solar system will transform. The gas outside the local bubble is cooler, with temperatures closer to a few hundred degrees Fahrenheit compared to the million-degree gas inside the cavity. It is also denser, packed more tightly with hydrogen atoms and molecules. Some regions beyond the bubble contain thick clouds of molecular gas, where stars form in bursts. Other regions are somewhat thinner, but still denser than the cavity interior. Picture leaving a warm, nearly empty gymnasium and stepping into a cool, crowded hallway. The change in air density hits you immediately. The temperature drops. The sound environment changes because the new space reflects noise differently. Everything feels thicker. For our solar system, the change would hit the heliosphere first. A denser, cooler interstellar medium would push on the heliosphere with greater force. The bubble would compress. The boundary Voyager crossed at 11 billion miles out could move inward by a substantial amount, possibly shrinking to half its current distance or less. Pluto, Neptune, and other outer solar system objects could find themselves much closer to interstellar conditions. Cosmic ray flux at Earth would rise significantly. The change in ambient gas would bring other effects. More neutral atoms would stream into the solar system. Some would interact with the solar wind to produce energetic neutral atoms, similar to what IBEX already detects, but at higher levels. More interstellar dust would reach the inner planets. Dust grains can affect the zodiacal light and, over very long timescales, possibly Earth's upper atmosphere chemistry. The sun's own radiation field would remain unchanged, of course. Our star would not dim or brighten because of the crossing, but the environment outside the heliosphere, the cosmic weather surrounding Earth, would be different enough that any biosphere would experience measurable shift. Some researchers have speculated about past exits and entries. The Iron 60 evidence and the local bubble formation suggest the sun has traversed significant interstellar structures before. Climate proxies from deep Earth history occasionally show anomalies that cannot be fully explained by terrestrial causes alone. Connections to interstellar environment changes remain speculative. Voyager cannot survive long enough to witness the sun's exit from the local bubble. The probe will run out of power within years, but the data it is sending back now calibrates the models that astronomers will use to predict what future crossings will look like. Every measurement of interstellar gas density, every plasma wave detection, every cosmic ray count contributes to a better understanding of how our solar system interacts with its surroundings. The crossing, when it comes, will be slow. No sudden event, no visible boundary, just a gradual shift in the pressure, temperature, and composition of the gas our heliosphere swims through. Long before we leave the bubble, smaller interstellar visitors have already been showing up in our inner solar system, and they are arriving with increasing frequency. In October 2017, astronomers spotted something impossible. A telescope in Hawaii picked up a fast-moving object on a strange trajectory. When researchers calculated its path, they realized it was not bound to the Sunday. It had come from outside the solar system, passed close to our star, and was heading back out into interstellar space. It was the first confirmed interstellar object ever observed. They named it Oumuamua, Hawaiian for scout or messenger from afar. Oumuamua was small, only a few hundred feet long. It was elongated, with a shape that looked more like a cigar or a pancake than a typical asteroid. It tumbled as it moved. Its color was reddish, consistent with long exposure to cosmic radiation. Most strangely, it accelerated slightly as it moved away from the sun in a way that could not be fully explained by gravity alone. Theories ranged from outgassing of unusual volatiles to, briefly, a now largely abandoned suggestion of artificial origin. The mainstream consensus settled on some form of natural outgassing from exotic ices, though the exact mechanism remains debated. 2 years later, in August 2019, an amateur astronomer in Crimea spotted another interstellar visitor. This one, later named Comet Borisov, behaved more conventionally. It had a coma and tail, clear signs of cometary activity. It looked chemically similar to comets native to our solar system, with some differences suggesting it formed in a colder environment. 2 interstellar objects in 3 years. After decades of searching and finding none, picture a vast highway where cars have been passing your house for millions of years, but you only just installed a security camera. The camera catches 2 cars in quick succession, and you realize you had no idea how much traffic was actually going by. The visitors had always been there. Now we can finally see them. Estimates based on the detections suggest interstellar objects may pass through our solar system in numbers greater than previously imagined. Some projections put the population in the inner solar system at any given time in the thousands, most too small or too distant to detect with current telescopes. The Vera C. Rubin Observatory, which began operations recently, is expected to dramatically increase the detection rate. The telescope will scan the entire sky every few nights at depths and cadences no previous instrument has matched. Interstellar objects that would have passed unnoticed before will now be catalogued routinely. Voyager's work at the heliopause connects to this story. The boundary between our solar system and interstellar space is where incoming objects transition from being shaped by external forces to being shaped by the sunday. Understanding the dynamics of that boundary helps predict how interstellar objects behave as they approach, how their surfaces respond to increasing solar radiation, and how their trajectories get modified by the heliosphere's plasma environment. Why are we seeing more of them now? One answer is technological. Better telescopes find more objects. Another answer may involve changes in our galactic neighborhood. As the sun moves through different regions of the galaxy, the density of interstellar objects varies. Recent stellar flybys, like Schultz's star, may have pushed additional material into our vicinity. The question remains partially open. Some of these visitors may not be just passing through. A few may have been captured by the sun's gravity long ago, and they may still be orbiting us today. Some objects in our solar system may not have been born here. The sun is massive enough to capture passing interstellar objects under the right conditions. A small object approaching with just the right speed and angle can get pulled into a bound orbit, especially if it passes close to Jupiter or one of the other giant planets. The giant planet's gravity can slow an interstellar visitor enough to trap it. The mechanics are well understood. What astronomers are still working out is how many captured objects are currently orbiting our sun and how we might identify them. Candidates have been proposed. In 2018, researchers studying the orbit of a small body called 2015 BZ509, a co-orbital asteroid of Jupiter, noticed its motion was retrograde, opposite to the direction most solar system objects orbit. Its orbit appeared stable over long timescales. The researchers argued the object's properties were best explained by an interstellar origin. It may have been captured by the sun billions of years ago and has been orbiting quietly ever since. Other candidates have emerged. Some distant trans-Neptunian objects have unusual orbital characteristics that suggest external origins. A handful of asteroids in unusual gravitational niches show properties that might point to capture. None of these identifications are confirmed with certainty. Each remains a hypothesis. Picture a fishing net dragged slowly through a river. Most of the water passes through without catching anything. Occasionally, a leaf or a branch snags in the net and stays there. Over a long enough time, the net accumulates a collection of caught objects, each one a visitor from somewhere upstream. The sun's gravity is the net. The interstellar objects are the branches. Why does capture matter? Because captured objects carry information about their places of origin. They formed around other stars, possibly billions of years ago, in environments we cannot directly observe. If we can identify and study them, we gain samples of material from distant star systems without having to send probes there. The chemistry of a captured object might differ from native solar system material, different isotope ratios, different mineral compositions, different organic molecules. A captured object is a piece of another planetary system, delivered to our doorstep by pure orbital dynamics. Current telescopes are not well suited to identifying captured interstellar objects by their properties alone. Most look like ordinary asteroids or comets. Dynamical analysis of their orbits provides the only strong clue, and orbits change slowly over time, blurring the original signatures. Future missions may help. Dedicated interstellar object sample return missions have been proposed. The idea is to send a spacecraft on standby, ready to chase down any newly detected interstellar visitor and collect material. The European Space Agency's Comet Interceptor, scheduled for launch in the coming years, is designed to do something similar for comets, with potential to target interstellar visitors if one appears at the right time. Voyager's work, while not directly related to capture detection, contributes to the broader picture of how interstellar material interacts with our solar system. The probe's measurements of the heliosphere's structure, the incoming interstellar wind, and the density of neutral atoms feed into models of how interstellar objects behave as they transition between external and internal environments. The captured objects represent one kind of interstellar interaction. A much larger kind involves the clouds of gas the solar system drifts through, and one such cloud ahead of us is denser than anything we have encountered in recent history. Far ahead on the sun's path, astronomers have identified dense regions of molecular gas. Molecular clouds are the nurseries where stars form. They are cold, typically only a few degrees above absolute zero. They are dense compared to the average interstellar medium, packed with hydrogen molecules, dust, grains, and complex organic compounds. Some contain young stars still in the process of formation, surrounded by disks of planet-forming material. Our solar system's trajectory through the galaxy may bring us into or near one of these clouds in the far future. The timing is speculative. The sun's motion is well measured, but cloud positions shift over time, and the detailed geometry of what lies along our path millions of years from now involves significant uncertainty. Some models suggest the solar system could encounter denser regions within 2 to 5 million years. Others push the timeline out to tens of millions of years. A few researchers suggest we may have already brushed past dense regions in the recent past, with the local bubble serving as one consequence of those encounters. Picture a ship sailing through mostly open water, but approaching a region of dense fog banks. The ship cannot avoid all the fog. Eventually, it will enter one bank, navigate through, and emerge on the other side. The fog changes visibility, changes the ship's speed through the water due to increased drag, and changes the environment inside the cabin due to humidity. Our solar system is the ship. Molecular clouds are the fog banks. What happens when the sun enters a dense molecular cloud? The heliosphere gets squeezed significantly. Models suggest that in a dense enough cloud, the heliosphere could be compressed so severely that its boundary retreats inside the orbits of the outer planets. In extreme scenarios, some researchers have proposed the heliosphere could contract to distances smaller than Earth's orbit, though this remains controversial and depends on cloud densities at the upper end of plausible ranges. If the heliosphere shrinks that far, Earth would be directly exposed to interstellar material. Hydrogen atoms and dust grains from the cloud would rain into the upper atmosphere. Cosmic ray flux would rise substantially. The solar wind would collide with interstellar gas much closer to the sun than usual, creating compression shocks near the inner planets. For Earth's climate, the consequences could be real. Increased cosmic rays might influence cloud formation and atmospheric chemistry. Interstellar dust could affect sunlight reaching the surface. These effects would depend on the density and composition of the cloud encountered, which cannot be known precisely without being there. Some researchers have tied past climate shifts to possible cloud encounters. Evidence is circumstantial. Correlations with cosmic ray proxies and isotope records suggest something happened during certain periods, but assigning specific causes to specific cloud crossings remains difficult. Voyager's measurements provide the baseline for these predictions. The probe's data on current heliosphere conditions, combined with models of how the bubble would respond to denser external environments, give scientists the tools to estimate future encounters. The dense cloud question is long-term. Nothing is imminent on human timescales. But the galaxy is not a passive background. It pushes, pulls, and occasionally soaks our solar system in material from its star-forming regions. Any such encounter would leave marks on Earth, and past encounters may have already done so. Earth's climate has shifted dramatically over millions of years. Ice ages have come and gone. Warm periods have stretched across entire geological eras. Transitions between climate states can happen relatively quickly in geological terms, over tens or hundreds of thousands of years. Most of these shifts are explained by terrestrial causes. Orbital variations change how much sunlight different regions receive. Volcanic activity releases or absorbs carbon dioxide. Ocean currents redistribute heat. Continental positions shift plate tectonics. Some researchers have proposed that cosmic influences also play a role. The idea is controversial but not implausible. When the solar system passes through denser regions of interstellar gas, several things can happen that might affect Earth's climate. The heliosphere compresses, allowing more cosmic rays into the inner solar system. Interstellar dust rains into the upper atmosphere, potentially affecting cloud formation. The sun's direct radiation output does not change, but the environment surrounding Earth does. Picture a greenhouse on a calm day. The temperature inside depends mostly on the sunlight and the greenhouse's insulation. Now imagine a slow-moving dust cloud drifts across the region. The cloud slightly dims the sunlight reaching the greenhouse. It also changes the local humidity and seeds more condensation on the glass. The greenhouse cools. The effect is small, but it persists for as long as the cloud is present. Some climate proxies show patterns that could be consistent with cosmic influences. Deep-sea sediment cores reveal variations in cosmic ray activity over millions of years, measurable through isotopes like beryllium-10 and carbon-14 produced by cosmic ray interactions in the upper atmosphere. Some of these variations correlate loosely with climate shifts. Other variations do not. The statistical significance of the correlations is debated. A few researchers have proposed specific scenarios. One hypothesis suggests the sun's passage through the local bubbles formation era, driven by nearby supernovae millions of years ago, contributed to extended cold periods on Earth. Another hypothesis links the Pleistocene ice ages, which began about 2.6 million years ago, to the sun's movement through a region of higher interstellar density. The iron-60 signatures in ocean sediments fall within this era. None of these links are established as causal. The mainstream view treats ice ages primarily as a product of orbital forcing, combined with feedback mechanisms involving ice sheets and ocean circulation. Cosmic influences, if present, likely play a secondary role. The most dramatic scenarios involve direct cloud entry. If the sun were to enter a dense molecular cloud, the effects on Earth's climate could be substantial. Increased dust inflow might reduce solar flux, reaching the surface by a few %, enough to trigger cooling. Increased cosmic rays might enhance cloud formation, amplifying the cooling further through higher planetary albedo. A few researchers have speculated that some of the so-called snowball Earth events, extreme global glaciations in deep Earth history, might have been partially triggered by cosmic environmental changes. This is deep speculation. The connection is not established. Voyager's data contributes indirect support for these discussions by mapping the current interstellar environment around the Sunday. Knowing how the heliosphere behaves today gives researchers better models of how it would respond to different external conditions. The probe cannot prove or disprove cosmic climate influences, but it sharpens the tools used to investigate them. The larger question remains open. Does the galaxy shape Earth's climate over long timescales? Most researchers think the effect is small. A minority think it is larger. Over even longer timescales, the galaxy's influence on our planetary orbits becomes harder to ignore. Planetary orbits are not eternal. On short timescales, Earth's orbit around the Sun looks fixed. It traces a nearly circular ellipse year after year, century after century. For all practical purposes, our orbit is stable within the span of human civilization. On long timescales, everything changes. Orbital mechanics in the solar system are chaotic over very long periods. The gravitational interactions between planets, especially the giant outer planets, cause their orbits to vary slightly over millions and tens of millions of years. Those variations compound. Earth's orbit becomes slightly more elliptical, then less, then more again. The axial tilt shifts. The timing of closest approach to the Sun drifts around the year. These cycles are known as Milankovitch cycles, named after the Serbian scientist who first calculated them in detail. They operate on timescales of tens to hundreds of thousands of years. They drive ice age cycles through their effect on how sunlight is distributed across the Earth's surface. Beyond Milankovitch cycles, even larger scale influences act on the solar system. The galactic tide, the combined gravitational pull of the Milky Way, exerts a constant faint force on every object in the solar system. For the inner planets, the effect is negligible compared to the Sun's dominant pull. For the outer solar system, especially the Oort cloud, the galactic tide is a significant shaping force. But over billions of years, even the inner planets feel subtle effects. Picture a spinning top on a table. Over seconds, it spins smoothly. Over minutes, it wobbles slightly. Over hours, the wobble grows as energy dissipates and small external forces accumulate. The solar system is the top. Galactic forces are the slow accumulation over cosmic time. Passing stars also matter. Over billions of years, hundreds of stars pass within a few light years of the Sunday. Most have negligible influence. A handful come close enough to perturb the Oort cloud. A very few, over the full age of the solar system, may have come close enough to subtly influence even the outer planet orbits. The stability of the inner solar system is not absolute. Numerical simulations run forward in time show that Mercury's orbit is chaotically unstable over billion-year timescales. In a small fraction of simulations, Mercury's orbit becomes so eccentric that it could collide with Venus or be ejected from the solar system entirely. This is not expected to happen within the Sun's remaining lifetime, but the simulations show the orbit is not predictable beyond a few tens of millions of years. Earth's orbit is more stable than Mercury's, but even our path around the Sun is subject to slow drift over very long periods. The galactic environment contributes to the uncertainty. A passing star, an encounter with a dense cloud, a gravitational wave from a distant event, all can nudge the system in tiny ways that compound over deep time. Voyager's contribution here is foundational. The probe's measurements define the current interface between the solar system and the galaxy. Every model of how external forces affect planetary orbits relies on accurate boundary conditions at the heliopause. Voyager provided those boundary conditions for the first time in history. As the probe approaches the end of its operational life, it is sending back the final pieces of data that will anchor these models for decades to come. And Voyager's final transmissions carry a warning that reaches beyond the solar system's current conditions. Voyager 1 will go silent soon. The plutonium that powers the spacecraft is running out. Every year, the probe loses about 4 watts of electrical output. Engineers have already shut down most of the scientific instruments to conserve energy. By the late 2020s or early 2030s, even the bare minimum of communication will become impossible. The probe will keep moving forever, but it will stop talking. Before that happens, Voyager is still sending home data. The final transmissions are a distillation of everything the probe has measured since crossing the heliopause. Cosmic ray counts, plasma density readings, magnetic field orientations, subtle shifts in the interstellar wind. Each data packet takes more than 22 hours to reach Earth. Each one carries a few seconds of measurement from a place no human will visit in our lifetimes. The picture the data paints is coherent, and it is unsettling. The heliosphere is being squeezed. The pressure from outside is rising. The interstellar wind direction is changing. The cosmic ray flux is higher than any time in recorded history. Our solar system is moving into environments our models were not built to predict. The protection our sun provides is real but limited, and it varies with solar activity in ways that leave periodic windows of greater vulnerability. Picture a ship making its final voyage before retirement. The captain transmits one last report to port. The report summarizes everything the ship has learned about the waters ahead, the currents, the weather, the hidden rocks. The ship will not return. The report is all that is left. Voyager is that ship. The interstellar medium is those waters. What is the warning? It is not a single dramatic event. Voyager is not announcing an asteroid impact, a solar storm, or an alien signal. The warning is slower, more structural. Our solar system is embedded in a dynamic galactic environment, and that environment is changing on timescales that matter for humanity. Thousands of years, tens of thousands. Not immediate, but not eternal either. The sun's protective bubble is thinning during current solar weakness. Cosmic ray exposure is up. Interstellar pressure is rising. We are drifting toward a denser cloud that will compress the heliosphere further. A large star, Gliese 710, is on a direct course to perturb our Oort cloud in roughly 1 million years, sending a possible rain of comets inward over the millions of years afterward. The galactic tide continuously reshapes the outer solar system. Unseen masses may be pulling on the most distant objects in our planetary family. None of this will destroy Earth tomorrow. Most of it will play out over timescales longer than civilization has existed. But the future of our planetary home is not isolated. It is tied to the galaxy. It is tied to events happening hundreds of light years away. It is tied to the slow drift of our sun through a living, changing Milky Way. Voyager's final message is that we live in an open system. We are not alone in space because we are constantly interacting with it. The probe is drifting now into silence. Its measurements will stop. Its voice will fade. But the data it has already sent and the insights it has already delivered will shape space science for generations. Decades from now, new probes will carry the story forward, and they will find a universe shaped by forces Voyager was the first to feel pressing against our fragile blue home.